So in order to define a security definition, I have to tell you what is a threat model. So we'll start with a very simple threat model. The threat model is as follows. I have Alice and Bob. Okay. They both have some secret key that they have sampled uniformly at random and shared. And now Alice wants to send over a message M. Okay. She encrypts and sends over the ciphertext. Bob receives the ciphertext. The adversary, there's an adversary. The adversary sees this ciphertext. Okay, and that is the real life threat that I want to model using a security definition. And let's make things even more concrete. Let's say this is a king instead of Alice and Bob. Let's say this is the king and his general. Okay, so they both shared a secret key, and this message can only be one of two things. It can only be attack at dawn or attack at dusk. Okay, this message can only be one of these two things. The king encrypts the message, sends it over. The general receives the ciphertext. The adversary has seen this ciphertext. Okay, think of it as the king sent this ciphertext through a messenger. The adversary intercepted the messenger and copied down whatever ciphertext the messenger had. Okay. Now I want to define security for this scenario. Okay. Right. So what do we want from this scenario? Okay, the adversary should not know. The informal goal is the adversary should not know or learn the message given the ciphertext, right? Yeah. Now, how do we capture the fact that the adversary does not learn M given the ciphertext?
The information of the adversary does not change.
Good. So I want to capture that the information of the adversary does not change given the ciphertext. Let's formalize it further. What does it mean that the information does not change?
The distribution, like the probability distribution remains the same,
0.5, 0.5. Okay, maybe it was not 0.5. Maybe the king is more likely to attack at dawn. Okay, but what we want to capture is the adversary knows that okay, the king attacks at dawn with probability p1, attacks at dusk with probability 1 minus p1. What do we want after it sees the adversary sees the ciphertext? Okay, this is some information that the adversary had before the king attacked. That the king attacks with probability p1 at dawn, with probability p2 at dusk. What do we want from a secure encryption scheme? The distribution does not change, right? Is everyone convinced that this is a reasonable definition? Okay, yeah. So that would be so informally what we want is whatever distribution you expect before you see the ciphertext, that distribution should not change even after you see the ciphertext. Okay. So this definition is good. I'll give you an alternate definition, and the point of giving an alternate definition is because this framework for giving definitions is going to be useful throughout the course. Okay, so this definition that I'll give you is via what we call security games. Okay, So the security game is defined with respect to an adversary. Okay? And for this particular scenario, I'll define a security game. The game is between a challenger and an adversary. The challenger samples a random key. Okay. There are only two messages over here. So it samples either M0 or M1. Let's say it samples a bit B. Okay. It sends over encryption of K sub MB. And the job of the adversary is to guess this bit B. Okay? So the game is as follows. Again, the challenger picks a random key, picks a uniformly random bit. Okay, so whenever I write this, it's always sampling uniformly at random from the set on the right. Okay? And the challenger computes an encryption of M sub B. Okay? Sends it over. The adversary has the ciphertext. The goal of the adversary is now to figure out whether M0 was encrypted or M1 was encrypted. Okay? Clear? There are only two possible messages, M0 and yeah. So for this scenario, there are only two possible messages. Let's look at the more complicated scenario. We'll look at it later. Okay? Is everyone? So now, when do I say that an encryption scheme is a good encryption scheme? Okay, so I have given a security game. Okay, how do I now define a good encryption scheme? Informally, what did you want over here? Here we had said, okay, the encryption scheme is good if the adversary's distribution of the messages does not change after seeing the ciphertext. Can you translate that intuition to this setting where we have a security game between a challenger and an adversary?
Each ciphertext uniformly sampled from the space is like equally possible.
Each ciphertext is equally possible. Okay, that is one way to characterize security. In terms of the security game, what do you want from the security game? Yeah, Rachit.
Probably that B dash is equal to B is half.
Exactly. Yeah. So, in terms of the security game, what we want is this ciphertext should not reveal any information about M0 or M1. Okay. Or, in other words, the probability of the adversary outputting the same B as B dash, this probability should be half. Okay? Clear? Everyone? What I'll leave as an exercise is to prove the equivalence between these two definitions. So you all gave me one definition where you all said the distribution of the messages should not change after seeing the ciphertext. Here we have a different definition. Okay, as an exercise, you must prove definition 1 is equivalent to definition 2. Does the question make sense?
But here we are assuming it's uniformly sampled from 0, 1.
Mm-hmm.
Whereas here we will, like, so what is the assumption?
Here we are saying no matter what was the distribution. So let me write this formally. Good.